All right, we will move on to sedimentary rocks. If you recall, sedimentary rocks are made from pre-existing rocks. So first we covered igneous rocks, which are made from molten material that's been crystallized. So that is where the rock cycle always begins. Sedimentary rocks have many steps in their formation, but they come from the weathered, broken down fragments of pre-existing rock that have been compacted together to form a brand new stone. Some sedimentary rocks, though, are organic in their nature. So they don't actually go through the process of taking pre-existing rock, stripping it down, and putting it back together. They do something altogether different. So we'll go over how sedimentary rocks are formed. Wind, water, ice, gravity, and other living things can cause rock to break in fragments. We call those fragments sediments. So weathering is the process of breaking down pre-existing material at Earth's surface into those sediments. What can also happen is chemicals can dissolve mineral fragments that are then carried away. So there is physical weathering or there is chemical weathering. So physical weathering would be wind, ice, gravity, living organisms, and to some extent water. But water primarily carries out chemical weathering, liquid water, that is. So in this picture here, we see this is a dry desert area, kind of looks like the southwestern United States. And this is a sedimentary rock formation, but it's being turned into new sediments. And then they will be, eventually, the sand grains or whatever that are produced from this will become new sedimentary rocks. So we're turning sandstone into sandstone. The wind blows sand, and the abrasion from that is what carves away parts of this structure here. As far as the chemical weathering goes, we see this river here. This is probably, I believe this is the Colorado River. So the bottom portions of the states of Colorado and Utah, or the northern regions of the states of Arizona and New Mexico, those four states come together at the four corners. And this is what the Colorado River pretty much looks like around there. Now we look at this water and look at how deep it has chewed into this solid rock formation here. But the water doesn't have much velocity to it. It's totally flat. If you would sit there and float, you really wouldn't be carried away with much speed. So how the heck can water do that? Well, rainwater and river water is just ever so slightly acidic, just barely. But that is enough to dissolve solid rock. Now, the thing is, it takes tens of thousands or hundreds of thousands or millions of years for rock to be able to chew its way through here. Now, this is also weathering because as that rock is stripped away, it doesn't turn into nothing, or it doesn't become nothing. It's still broken down. It's there. It's just microscopic, and it can be carried away and deposited into new stone. Ice, glaciers particularly, act as gigantic bulldozers. So this mountain chain here, the only reason it has valleys is because these huge ice structures, these glaciers, have taken that solid rock and pulverized it and carried it off. So here's what a glacier valley looks like after its glacier has melted away. And then gravity. Gravity is the agent that pulls, it dictates where the water flows. It dictates how the glacial ice flows. But it can also simply just carry material away as well. And then living things. I can see here a tree splitting a rock apart. But really, bacteria, fungi, and moss and lichens are really what produce the sediments, because they're so much more numerous than everything else, and they're present everywhere, and they're just constantly at work. So after weathering is the first step in creating a sedimentary rock. Then we have erosion. So erosion is the actual process of transferring the material away, and erosion is carried out by the same mechanisms as weathering. although not really by living things. Living things aren't really responsible for erosion. After erosion, that will take us to deposition. So the fragments, the sediments or whatever are dropped. Big ones don't go very far. Really fine particles can be carried thousands of miles. As those layers are deposited, they become hundreds to thousands of feet thick, and the pressure that is the result of that is crucial in the next steps that come up. So here we see, a river. Why do rivers look so dirty? Well, because they're carrying huge amounts of sediment within them. Sandstorms can transport material far and wide. We have, if you've ever been to around the area of Sioux City, there's a place called Council Bluffs that's kind of near there. What is a bluff? A bluff is a big type of hill, but bluffs are made out of huge deposits of wind-blown sand and silt, basically. So a bluff is like it's not exactly a sand dune because there's lots of vegetation growing on top of it, but that's actually how they're formed. With all of that pressure, what happens is the layers begin to squeeze the older sediments down below. Now, the sedimentary rock cannot form. If you would go to the largest sand dune in the world, there are sand dunes in Africa that are more than 1,000 feet tall. If you could somehow get all that sand out of there, you wouldn't necessarily find in the core of that huge sand dune the sand has been pressed into solid rocks. It doesn't exactly work that way. You have to have water present because it's going to act not really like cement, but it's kind of similar. So you can picture, let's see if I can draw a picture. Well, no, I won't draw it because there's a picture of it coming up. You can imagine sand grains. They're very small, but water can fit into almost any size space. And inside that water are dissolved minerals, especially quartz and calcite, because those are just some of the most common minerals. Now, as the sediments are squeezed, the water is forced out. We say that it's exuded, but the minerals are not all forced out. So what happens is, now that the quartz and the calcite are not floating, dissolved in the water starts to go away. The quartz and calcite will start to cling to the surfaces of the sand grains, all the billions and billions and trillions of them, and they will start to grow outward, and they will mesh together and interlock. And that is the bonding agent. That is the cementing together of those mineral grains, of the sediment grains, sorry, I should say. And this is the actual cementing process, but we call it lithification, which just literally means to turn into stone, to lithify. Now, when you actually make cement, it's a completely different process. Yeah, you take broken up gravel and really fine powder, that is the cement mix, and you mix water with it. But when you make something out of cement, like a sidewalk or a curb, the water doesn't actually go away. You're not waiting for the water to evaporate. The water does a chemical reaction with the cement, and the water molecules are broken apart and then bonded to it. So it's not like it has water in it. The water's been changed. Like when you bake a cake, you don't actually say that the cake still has raw egg and flour in it. No, those have been chemically changed. So it's not, there's really, none of the egg is still left. But that's cement, so we don't have to talk about that. Here, this picture illustrates it. So here's before the extruding process happens. We have, why is this going in two different directions? It doesn't really matter where we go, but we'll go this way. So we have water in between here. So this would be magnified hundreds of times because we're making sand and silt grains visible to us. But anyways, these layers are then compacted, they're squeezed together. And as that happens, the water is forced out, but these minerals can start to grow on the surfaces now. And eventually they just grow into each other and they interlock. And so it's been lithified. And sedimentary rocks, I mean, technically they form kind of below the surface, but they form really on the surface, so we say they're surface-forming rocks. Now, as this process goes on continuously, there are places such as the Grand Canyon. Not all of the Grand Canyon is sedimentary rock, but I believe most of it is. The Grand Canyon's a mile deep, and it represents something like 1 billion years of Earth's history. So these processes, they just never stop. In some places we have a huge timeline that's been preserved. But anyways, those layers will not all be uniform, so we call that strata. The distinct layers are known as strata. So this person sitting here, also the rate at which layers are dropped down greatly changes too. So I hope you can make this out. If we look here, the layers by this person, we have a yellow, a red, a white, a red, a brown, a red, a white, a pink, a white, a red, kind of a brown, a light tan, a dark tan. Here we actually have a green color. There's it's green up here as well. There's a huge variety, right, in this first half of the layer here. So if you remember from the first discussion, sedimentary rock gets its different colors because there are multitudes of different minerals present. But some sedimentary rocks form on in the beds of shallow seas or oceans or lakes. Others form on dry land. And the dry land can have different ecosystems. Now, if the environment is shallow water, well, the chemistry, the types of chemical reactions that go on, and the types of minerals that form in water is way different from the types that form on land. But even on land, because there are different ecosystems, some land is very dry. Other types of land biomes have more moisture. So again, different chemical reactions, and there are so many different minerals on our planet because there are so many different environments and natural resources and physical conditions for forming different kinds of minerals. So the different colors tell us that this area has been experiencing lots and lots of different changes in the kind of environment. We can't say definitively just by looking at it what it was, but in general, when you see red, the red gets there from oxidation, so like iron or rust forming. Rocks naturally have some iron in them, so this area right now, if we look at the very top layers of rock, those are the most recent. The deeper you go, the older they are. This area looks like kind of a dry, I mean, these plants aren't doing too well. So this is a dry area, not a lot of soil coverage, not a lot of vegetation coverage. So the oxidation, the rusting kind of the rocks is exposed. So lots of the red layers, we could probably assume that's what's going on. These green layers, when you see green sedimentary layers, that's usually indicative of there are certain types of clay that when they turn into sedimentary rock, that's the color they get. And those clays only form under water, but not like deep ocean water, lakes, so not very deep. Another thing here is we have a huge number of layers from here to here, but then if you look up here, we have far fewer layers, and we'll actually look right here. This layer is totally uniform from here all the way up to here. So that could mean a few things. It either means that whatever was going on to form this layer stayed stable, so the environment did not change for in an incredibly long period of time. Or what's also possible, we don't know just by looking, is that maybe it wasn't stable for a very long time, but for some reason, the rate of deposition during that time was just much, much, much greater than it was in all these other layers. So that's the evidence that sedimentary rock gives us. It lets us understand the history of our planet. And this is a really fascinating place. I can't pronounce it. It's in China, and it's got lots of X's and I's and Z's in the name. I don't remember it off the top of my head. But hopefully you can see, look at all the colors that we see on these. Now they're not horizontal anymore, but if you look at each layer, they are parallel to each other. It's just that they all happen to be at a 45-degree angle. Originally, all these layers were flat, horizontal, because sediments in the deposition process, they just naturally drop and are flat. Plate tectonics, China is one of the most mountainous countries on the planet. Plate tectonics has pushed these up by plates converging into each other, and now it's tilted. Okay. So we need to take sedimentary rocks and classify them so we can understand what the conditions were that formed them. And that's basically how they are classified, by the way they're formed. So clastic sedimentary rocks are the majority of sedimentary rocks you find around our planet, and they're the ones that form from the steps we covered before. Pre-existing rock, it's weathered down, it's eroded, deposited, compacted, cemented together. And then we will further classify these by the sizes of the sediments in them. So just like texture in igneous rocks, the texture of sedimentary rocks is also taken into account. So basically, we put them in really broad groups, but there are many examples of each of these. Conglomerates are like large pebbles mixed in with smaller sediments glued together. Sandstones, it would have a pretty rough texture to it, like sandpaper would, like 200 or 100 grit sandpaper. Siltstone, silt is much, much finer than sandstone. So a piece of siltstone would actually feel very smooth, or fairly smooth, but kind of like a cement brick feels like the gray cinder blocks. Those feel pretty smooth, but I mean, at the same time, you know that it's not really a smooth surface. Shale, those are the absolute finest grains. So sometimes tabletops can be made out of shale, and they can be polished very, very, very smooth. If you just the desks we have in our classroom, they're not made of shale, but that's the kind of texture that it has. It's not glassy or polished by any means, but it's very fine grained stuff. So here's a conglomerate, like you can really easily see the big pebbles and rocks mixed in there. This would be a sandstone. I'm not sure how well you can pick up the texture of it, but we have this stuff in class that we can look at as well. It's just rougher. Siltstone is even finer than that. You probably wouldn't be able to see unless you had a magnifying glass the sediments that make it up. And then here's shale. So you'd probably need a stereoscope or a microscope to actually see the sediments. But they are there. If you would feel it with your hand, even if you can't see the texture, you can feel the texture. It's definitely not glassy or polished. Right, the other types of sedimentary rock are chemical sedimentary rocks. So these form when the minerals crystallize directly from water. So there is no compaction that goes on with this step. The rock can simply form in water all on its own through different kinds of chemical reactions. This is how fossils are created. So when you pick up a fossilized bone, the bone is not there anymore. There's no more bone tissue. Instead, what happens is bone, if you look at it under a microscope, or if you can actually just pick up a bone if it's broken, it's very spongy. What happens is water that is rich in minerals gets into all the nooks and crannies and pore spaces of the bone, or wood, same way. Wood is very porous. And the minerals can crystallize inside of those spaces, and then eventually so much time passes that all the organic matter simply dissolves away, but a casting or a casing of the shape of the bone or wood or tissue, whatever it is left over. That's your fossil. Limestone is also made that way. Animals take in mineral nutrients and they build their shells, or coral reefs build. Corals don't really have a shell. And a coral reef is a colony of many, many thousands of individual organisms. They're called polyps. They look like tiny sea anemones. You'll have to Google coral reef polyp to see what I mean. Now, they don't have a shell, but they build a calcium carbonate structure around them, and that's what the coral reef is. That's basically what we see. Now, those coral reefs, because they're made of mineral, they get left behind even if the coral goes extinct. And so that compacts into these huge limestone formations. And rock salt, because it's just formed when we learned about minerals, a precipitation reaction is what forms salts and lots of halides. Well, if you have rock salt mixed in, or salt mixed in with other types of rocks, then it's a sedimentary rock. And it's a chemical sedimentary rock. Yeah, that's just a little bit more of a distinction. So here's, this is limestone. Now, it's not very obvious by looking at it that it's made from seashells or anything, but scientists can analyze the minerals in here, and we find mostly calcium carbonate, things like that. And we understand now where it comes from. What helps is, I don't have a picture of it right now, I guess, but there's such a thing as fossiliferous limestone too, and you will actually find embedded within the rock seashells, because the shape of the shell is maintained because it was made of minerals and it gets preserved there. There are other organic sedimentary rocks, so they fall outside the norm of all other rocks, but coal is formed from once living plants. So rather than the plant becoming fossilized, instead, because when it's fossilized, all the organic matter is destroyed. Coal instead, now coal is also millions of years old, but the organic material is sort of preserved. It's not still wood when you pull it out of the ground, but wood is made of carbon and hydrogen for the most part. Most of our bodies are made of carbon and hydrogen and oxygen. So the elements that were in the wood are left over, but it's been reduced down into just, well, it's not plant matter anymore. It's just simply rocks at that point. And then limestone is, now these are also chemical sedimentary rocks. We're just kind of talking about the examples. Limestone's made of plankton, these things called diatoms and radiolaria also, but also seashells. For the most part, it's made of single-celled material, though. I do have a picture of it. So here's fossiliferous limestone. You can see this whole thing is just caked in seashells. Other times you find only a few seashells mixed in within there. I've been talking about this already, but sedimentary rocks form those distinct layers because that's indicative of the environment they formed in. Depending on what's present, how much water, how little water, the above ground, dry climate, whatever. Different kinds of chemical reactions happen in different kinds of environments, so that produces unique minerals and unique colors in the strata. So stratification is simply the building up of many different layers. So lithification is the formation of just sedimentary rock in one place at one time. Stratification is eons and eons of lithification. But those stratified layers give us a timeline that shows geologic events. In chapter 12, we will dive deeper into this. But you can find, for example, if one layer, we've seen pictures of this, where we have a rock layer where all the sedimentary layers are tilted at a funny angle, and then above that, so let's just draw a rock formation here. And then above that, the rock layers will be tilted, or they're not tilted. They still have their original horizontality preserved. Well, that tells us that between here and here, something was going on. There was plate tectonics that shifted this layer, and then whatever was going on during this period down here ceased or stopped, and then new layers were put down. So that's an example of that. But also, how do we know that, I'm looking for an eraser, how do we know that an asteroid took out the dinosaurs? Because the dinosaur fossils are preserved in rock all around our planet. I have a cloth somewhere here. But you do not find dinosaur bones everywhere on our planet. There's this thing, so let's say, for example, we have a dinosaur bone right here, And from this layer above, we have never found any dinosaur bones. Well, what the heck's going on here? It means something here is the cutoff for our dinosaurs. Well, all around the globe, you can find it everywhere. There's this really distinct dark layer. It's called the KT boundary. And what scientists have done is they've taken material out of that layer and analyzed it. And they find this element in there called, oh shoot, what's it called? It starts with a U. Or no, it doesn't. It starts with an I. It's called iridium. You've probably never heard of that element because it's extremely rare. We really don't, it's not a household name by any means. Iridium on Earth is incredibly rare, but in meteorites, it's very, very common. So the entire Earth, in most places, you can find this layer, and it's been dated to 66 million years. So the whole planet got blanketed in iridium. Well, how did that happen? The only logical explanation is a very large asteroid that hit, and then when an asteroid hits the Earth, it's going so fast that it's destroyed in the process. So a plume of material went over the planet, and then that spread all around the globe. Right now, there are these massive, record-breaking fires happening in California, and for the last several days, you go outside, and the whole sky is cloudy. California is 1,200 miles from here, but the smoke is getting over here. Okay, now imagine an asteroid the size of a mountain. Yeah, that material is going to spread around the planet. And like we said, above that layer, above the KT boundary layer, we've never found any dinosaur bones because they all were killed from that asteroid impact. Now, along with that, the fossil record also shows us that life has changed in the past. I think I mentioned this in the first chapter. For the longest time before Charles Darwin, the conventional wisdom was all the plants and animals that we see on Earth were created or have always existed. There have always been people on Earth, and there have always been llamas and pine trees and whatever on Earth. Well, now we know better because we've looked at the fossil record. There used to be these things called dinosaurs. And we've known about dinosaur bones for a long time, but really in the 1800s is when they were studied intensively. And people today still will say, you can go on like answersingenesis.com and they will tell you, yeah, man and dinosaurs coexisted because they dig their heels in, they say man has always existed, they were created on the 6th day or whatever it was, and that means that we had to have been there with dinosaurs. If there are dinosaur bones, then that means there were dinosaurs and people. Totally wrong, if that wasn't obvious, but there we go. So we see in the rock layers groups of fossils that do not mix together. You will never find human, and there are places on the Earth where we have literal dinosaur graveyards, like hundreds or thousands of specimens that all died in one area. In the Black Hills, we have the mammoth site where there are dozens of mammoths, which obviously aren't dinosaurs. But guess what? That site is very, very old, and there are no humans in there. There are many different species of animals, no humans. No human bones have ever been found in proximity with dinosaur bones, for example. And similarly, no woolly mammoth bones have been found with dinosaur bones. So we know that there's a progression of changing species. This is just to show you layers. And again, layers down here are older, and they get younger as you go up. And this is another example of geologic events. So we can see these layers have been tilted. These layers have actually been broken. There's a new deposit of igneous rock down here. So this shows us that this area has been experiencing lots and lots of changes over a really slow period of time. Because this all could not have been formed in one single event. Actually, if I want to pick on the Answers in Genesis people, they will tell you that even though these layers are at different angles. These are at a different angle than those, and these are at a different angle than that, and we have a breakage here. They tell you that their website will say that, yeah, that can happen all at once. And they say the great biblical flood is what dropped all these sediments down and somehow got them mixed all up in different orders. Oh well, not everybody can be right, but we can, because we're doing science. Thanks for listening.